has been at Cambridge and Princeton University, and is a very prolific mathematician in all kinds of broad areas of mathematics. But I think the most telling thing that I found to say about him is something that I found on the internet. And this is a quote from John. I guess I'm not so much a mathematician as a teacher. In America, kids aren't supposed to like mathematics. It's so sad. People think that mathematics is cold, but it is not at all. For me, the whole thing is sensual and so exciting. John will talk about triangle geometry.
Okay? Well, it's okay if I keep my head down, probably, but not if I don't. I thought you were going to say something else, because there was another quote that I really like, which is, I'm not so much a mathematician as a teacher. And then it carries on to say, if it sits down, I teach it. If it stands up, I teach it. But if it runs away, I might not be able to catch up. But I'll try. So if you run away, I'll still try to teach you. Well, I think it's a disaster what has happened to geometry in high schools. And in a way, I feel a little bit guilty. Like everybody else at a certain time, I was against the enormous amount of projective geometry that was taught in, well, at least in my university, and I know in lots of others a long time ago when I was a student. We thought there was too much of it. And there was a sort of reaction against geometry. And then, of course, the products of our universities and colleges went out and taught in our schools, and they didn't know any geometry, or they sort of felt the geometry was out of date. And they stopped teaching geometry in schools. Well, not quite, but sort of almost. And now we have this really rather terrible situation, it's been the case for some time, where there are these awful proofs, two-column proofs. I'd never heard of a two-column proof until I came to this country. In fact, somehow I managed to avoid learning about it until rather later. Terribly stifling things, but particularly stifling now, when you don't get anywhere. And so you have some elaborate arcane ritual of proving things, and what you're proving is that if the two angles are equal and the two sides are equal or something, some utterly boring little fact. Now, when we did teach geometry, there were some interesting facts, and they're still interesting, and now that Geometer, Sketchpad, Cadbury, and things like this are coming all over the schools, we're seeing a revival in geometry. And I want to, so to speak, lead it, although I suppose I'm leading it from behind to some extent. One of the ways in which I personally am behind is that I myself don't use any of these tools. I was been interested in geometry for a long time. But I want to call your attention and everybody else's attention, the school kids' attention, to the wonderful things that there are in geometry. So let me just, particularly in triangle geometry. Well, let me just go very quickly through a few things. Let's take the standard centers. So here I have a triangle, A, B, C. One theorem is that these perpendicular bisectors meet. And of course, the reason they meet is that each perpendicular bisector is the locus of points that are equidistant from two vertices. And so the place where they meet is the point O that's equidistant from all three vertices. So that's the circumcenter. Now let me draw the center of gravity. You just take the three lines, the medians joining the vertices to the midpoints. Let me just mark off the fact that those two lines are equal there, and we get the center of gravity. Let me then proceed to the orthocenter. Which is where these three perpendiculars meet. And then, let's talk about the wonderful 9-point center. The author said it was supposed to be called H. I'm going to draw the 9-point center a little bit bigger. Very nice old that. What we do here is we draw these three perpendiculars, which define this point H we just spoke of in the previous thing. But now we mark the midpoints of any two of A, B, C, and H. So they're the midpoints of the edges, but I'm also going to mark the midpoint of BH, and the midpoint of AH, and the midpoint of CH. So those are 6 midpoints. And then I'm going to mark the place where AH meets BC, the place where BH meets AC, and the place where CH meets BC, and remark that these are the wonderful 9 points of the 9-point circle, which was really discovered by Euler, except that he only noticed 6 of the points. It's a very old theorem, and in fact, the easiest proof adds another 3 points, and makes it sort of seem obvious. But it's a bit of a shocker that those 9 points lie on the circle, and the center of that circle is called the 9-point circle. And astonishing fact, let me draw the Euler line. Well, I'll just draw it in abstracto here. These 4 centers, which I'll give the colors that I gave them a moment ago, always lie on a straight line. And not only that, they're always in the same proportion, 2 to 1 to 3 on that straight line. So that's the Euler line. So there are the sort of 4 Eulerian centers and the Euler line that they lie on. Well, I'm interested in theorems like this, first because I think anybody who hears this is quite interested in this anyway. It's a bit of a shocker. But then, you know, there was, in the 19th century, a tremendous amount of development of this triangle. Enormous numbers of points and circles to study. I'm going to mention a few of them. I'm trying to organize them. I've been trying to organize them on my own account, but more particularly because I want to publish a book. Let me tell you about the book. The book's going to be called The Triangle Book. And one nice thing about this is it's actually going to be a triangle shape. Well, that I think, I hope anyway, will multiply the sales by 3. I mean, no bookseller will be able to stick it straight in the shelf, so they'll have to stick it outside, and then people coming along will think, triangular book, and some of them will buy it for the novelty even if they're not interested in triangles. But then maybe one or two of them can be seduced into opening the book anyway. What they find, I hope, won't disappoint them, but I'm confident that it will, in fact, very often, because they'll find too much about the triangle. My book, which, by the way, I'm hoping to get Richard Guy to write with me, is not really a book addressed to the market that I want to reach. I want to reach the high school kids, okay? I don't feel confident to write to the high school kids. And what I'm hoping is to write for some of their teachers and for some of the people who write books for the high school kids and so on, curriculum developers and stuff like that. So I want my book really to be a sort of encyclopedia of everything there is about the triangle. Also, my book's going to contain all the proofs, and it's going to give the game away too often. And I think the proper thing to do at the high school level is to experiment and play and so on. But, you know, if you want to develop everything, if you want to say everything, you really can't afford to waste a lot of time playing, and so the book isn't going. But still, I hope it will have a good effect. Let me perhaps move on a little bit. Let me say one of the organizing principles here is this wonderful concept of sub and super triangles. Let me just explain that. Let me take a big triangle here. So that's the original triangle. And now I'm going to take its midpoint triangle, and the triangle you get by rotating the original triangle around the centre of each of its edges, and sticking it back on again. So in other words, you stick 4 copies of the original triangle together. So this is the super triangle, and this is the sub one. They're known by other names in many books. There are quite a number of them. This big one is sometimes called the anti-complementary triangle. What a terrible name. I want a nice short name for this. The sub-triangle, which is actually a sub-triangle of the original, and the super triangle. Okay. Why are these useful? Well, I'm glad you asked. You see, one of the ways in which they're useful is that if I erect the perpendicular bisectors to the edges of the super triangle, they are in fact the altitudes of the edges of the original triangle. So another way of saying that is that the orthocenter is the circumcenter of the super triangle. Okay? Which is rather nice. So let me just write that again. O equals, which way around is that? Oh no, I wanted to say it there. H equals super, the super orthocenter. The orthocenter of the super triangle is H. That's what the altitude means. Well, another thing that you might note is that 3 of the points I picked out for you, let me mark them in blue, 3 of the 9 points that are asserted to lie on the 9-point circle are actually the midpoints of the edges. And they are the vertices of the subtriangle. And so we have another assertion that n equals sub O. Okay? The 9-point center is the circumcenter of the subtriangle. Let me just draw that subtriangle in there. Well, this turns out to be a relationship that persists to a tremendous amount of interesting geometry, which I'm going to just discuss in a moment. What's it tell us, though? It does actually prove Euler's theorem. And let me explain why. If I take my triangle, and you take, say, this black triangle, turn it upside down, and then shrink it by a factor of 2, I get the red triangle. Or if I turn it upside down and expanded it by a factor of 2, I would get the blue triangle. So what does that say about the positions of O, G, N, and H? It says, if I, by the way, the place I'm turning about is G. So I'm going to put my pen, or I'm going to try and put my pen on top of G, and turn this thing around through half a revolution, and then shrink by a factor of 2, and I'll get from O to N, or if I expand it, I'll get from O to H. So in other words, what that says is that N is on the opposite side of G to O, and half as far away, and H is on the opposite side of G to O, and twice as far away. And that proves Euler's assertion, those 4 points are on a straight line. So that's a very, very nice organizing principle. Let me just show you a few more interesting centers. We have the incenter. Okay. I actually have an elaborate system of names for points. I call that I0 because there are some other points that are just as interesting as the incenter. And I think of them as other incenters, although their official name is excenters. Not very well drawn here. There are actually 4 of these points, and they're all algebraically the same thing, because in order to locate I0, you have to solve 2 quadratic equations, and so they have 4 roots. Okay, so there are the incenters. And of course, you know them as where the angle bisectors of the triangle meet. But here's another point that's moderately interesting. take a point here, take a triangle, and go halfway round its perimeter. Okay? So I want that left-hand side to be exactly the same as the right-hand side. Well, actually, you'll get to precisely that point where the outer X circle, the lower X circle meets the thing. And there are some other points here where the other two X circles meet. And they have this wonderful property that each of those 3 points is halfway around the perimeter. Halfway round. And now it's a nice little theorem that they meet. And that's a point called the Nagel point. And I'm going to put a plural on Nagel point because, in fact, there are 4 of them, just the way there are 4 incenters. There's another thing you can do. Make your triangle out of really heavy wire. Okay? And consider the center of gravity, so of the wire frame, speaker point. So it's the C, G of the frame. The center of gravity of the entire lamina, we discussed before, that was called G. And now take the center of gravity of the wire frame. Well, actually, that's one of 4 speaker points too, if the one I call S naught, therefore. Well, surprise, surprise. These 4 points here. Well, which 4 points? The incenter, the speaker point, and the Nagel point lie on the straight line. And the distances are 2, 2, 1 to 3 again. Why is it? Well, let me very quickly explain why it is. Will I bother to explain? I don't think I'll just make a little remark. The speaker point here is actually the sub-incenter, the incenter of the sub-triangle. And the Nagel point is the incenter of the super-triangle, when you work it out. Not immediately obvious from their definition, but true after a little bit of geometry, and I think very interesting. Well, I just gave you that as... Sorry? I just gave you that as...
Is it a homogeneous triangle boundary?
Yes, it's supposed to be uniform material. So those are, some interesting points. Let me come on with some of the really landmark theorems. By the way, I don't know how much time I have. Can't do all that much. No? Let me just come on to a few of the sort of really landmark theorems. Well, 2 theorems that I've always loved are called Napoleon's theorem and Morley's theorem. They all both concern equilateral triangles. Napoleon's theorem is you put an equilateral triangle on each edge of a triangle, and then it says their centers form an equilateral triangle. It's a beautiful fact. So this is Napoleon's theorem. It's one of the least held-regarded secrets that this is nothing to do with Napoleon, except for the fact that Napoleon was a pretty competent geometer. Maybe he could have found this theorem, but the first time it was called that was, I think, already this century. But still, Napoleon's theorem is as good a name as it is for any other one. And Morley's theorem. Morley's theorem, we trisect the angles and continue these lines until they meet. And then the theorem is Morley's. It's called Morley's trisector theorem. That's an equilateral triangle. This is notorious, well, it was notorious for being very hard to prove. When it was first produced, Morley didn't publish a proof until it languished for about 10 years, until somebody found an analytic proof. Then Morley did write a paper with a sort of proper proof in and so on. But you'll never see a proof as nice as this one until you open the triangle book. This makes it absolutely trivial. Let me just say what you do. So I'm going to let the three angles of this triangle be phi alpha, phi beta, and phi gamma. And then I'm going to let theta plus mean theta plus 60 degrees. Okay? That's just so that I can write quickly in here. So this is going to be alpha plus and gamma plus. Oh my God. Alpha and gamma plus plus, alpha plus plus and gamma, beta plus gamma plus, alpha plus beta plus. Okay. Then what I want you to notice is that, I could even mark the inner triangle, but what I want you to notice is that there are triangles of those shapes. Because if I add up the three angles, I always get 180 degrees. In any one of the little triangles, I've got this picture. I'm not saying this is what happens yet. We don't really know. But there exist triangles of those shapes. Now I'm going to tell you, I've told you what they are up to shape. Now I'm going to tell you what they are exactly in size. And I'm going to do that by demanding that all these red lines shall have the same length. These angles here are both beta plus. Two angles at the base of that. Well, you see, as a consequence of that, this bottom triangle here is isosceles. And therefore, automatically, these two lines have the same length. I want you just to scale it until that's the same length as all the other things. But I want you to make these 7 triangles separate. I can't do that easily in the picture. You do it in sketch now. And then I just want you to notice that they fit together. And the reason they fit together, for instance, is that this triangle here has angles beta plus, gamma, and therefore it must have an alpha plus. And so does this one. It has beta plus, gamma, and alpha plus. So they're similar, and therefore they're the same size too, because I made corresponding edges both be red. And so what I'm trying to say is that this edge of this triangle is the same length as it is of this triangle. And therefore, if I make them this size, I can just fit them together. And the argument says, so you can make 7 triangles like this, fit them together, and you'll get a triangle similar to the original one. So, I was going to mention one other really famous theorem, the Feuerbach theorem, because it's an absolute beauty. Let me just introduce you to it very, very quickly. What I'm going to do now is take the orthocenter and reflect it in each of the sides. Oh, sorry, it's not the orthocenter, it's the circumcenter, and I mispositioned it a bit. Yeah. Okay, so reflect it in each of the sides, and then I can see a rhombus forming here, and another rhombus here. Oh, damn, that wasn't very good picture. And another rhombus here. Okay. And I can complete this until I get a picture of what looks like a cube. It would look distinctly better if I'd drawn it a bit better. And this object here is the orthocenter. What that tells you is, I mean, all these lines are the same length. All these lines that I was busy drawing in red, I'm sure the original triangle in black. All those red lines are actually the same length. So this cube picture exists. And it shows you that the 3 reflections of the circumcircle in the edges all pass through H. It's a nice theorem. Sorry, I haven't drawn it very well. Reflect the circumcircle in the edges, and the 3 circles you get pass through H. Okay, well, if you think about it, you'll see that the 9-point center is the center of this cube. Let me explain why. Here are my points A, B, C, and H. I told you to take one of my points to be the midpoint of AH. But that's the center of a cube face. You see it? And what actually happens are the 6 centers of the cube faces are 6 of the 9 points that I told you about. That tells you that the 9-point circle belongs equally to this set of 4 points. I defined it in a symmetrical way in terms of A, B, C, and H, which are 4 of the vertices of the cube. Let me circle them in blue so you can see them. They're in fact one of the 2 tetrahedrons described in the cube. Okay. Well, Feuerbach's theorem tells you that the 9-point circle, as it was originally stated by Feuerbach, touches the incircle. Okay? But I want to make a remark. The 9-point circle touches the incircle, therefore it touches the x circles, because they're just the same. So the 9-point circle actually touches 4 circles. But then it was defined symmetrically in terms of A, B, C, and H. So the 9-point circle touches the 4 incircles of each of A, B, C, A, B, H, B, C, H, A, C, H. That's 16 circles. And also touches the incircles of each of O, A prime, B prime, or I'll call this A prime, B prime, C prime, etc. So we get 32 circles in all. And it's the 9-point circle for ABC that tells you it goes to the 9 points. It's also the 9-point circle for A prime, B prime, C prime that tells you it goes to another 9 points. They actually overlap. It altogether goes through 32 circles and 12 points. Well, I only discovered that number of circles and points comparatively recently. When I was at school, I knew about 16 of them. And I drew a figure which consisted of the 16 circles and the 9 points, but no 9-point circle. But you can see where it was. Because, you know, it's near this circle, and then it passes over to being this circle. It's just drawn by its abscess, which is a really very beautiful thing. Well, you know, I'd like to see a figure of these 32 circles and 12 points, all carefully marked, so you can see what it goes through. The Morley triangle is one of 18 triangles that are all equilateral and all parallel to each other. It's an absolutely gorgeous subject, this one. And, well, I don't know what I'm trying to say. There's an enormous amount of it. I want to write it all into a book, and I want lots of it to get into the high schools. Perhaps I don't want lots of it to be sort of taught into the high schools, but to be there to play with, so that, you know, an individual student can study some particular aspect. I better go on. Projective geometry. Yes, well, I'm sort of sure at the beginning you decried it being lost. Well, I didn't actually decry the loss of projective geometry. I will if you ask me to, because I'm sort of sad.
Wrote down the word disaster.
Yes, I know, it wasn't a disaster that we lost so much projective geometry. I think we really were doing too much of it. As I said, I was partly guilty, but the effect was not that we just lost projective geometry, we lost all geometry, which is absolutely terrible. Yes, I would like to see some projective geometry back. And I think one of the nice things is we could actually do it in the high schools, for instance, projective geometry. I mean, you know, if you see a railway track going away from you, into the distance here, what's the law of progression of the spacing of the sleepers and the ties? No? Anybody know? It's not arithmetic, it's not geometric either. Well, there is a nice little question that's really part of projective geometry. The cross ratio of any 4 consecutive ties is the same as the cross ratio of any other form of technique, such as this, how you might find cancer. Yes, I'd like to see lots of projective geometry. By the way, this is something I didn't get on to saying. Since I spent a lot of time drawing a picture, I feel I really ought to. Because one thing I discovered just over Christmas, which has revolutionized my thinking of triangles, it's the entire space of triangles. You take an equilateral triangle on the equator, and then stereographically project from an arbitrary point, and you'll get an image. And as you vary the point, the projected triangle varies in shape, and you can see a few of them drawn on the sphere there. So that the triangle corresponding to the North Pole is an equilateral triangle. It's an equilateral triangle described in the positive sense. The triangle at the South Pole is an equilateral triangle described in the negative sense. There's one shape of triangle for each point of the sphere, including 7 degenerate triangles on the equator. And this is a really wonderful picture because this sphere is not only the space of all triangles, but it's actually the plane of each individual triangle. You see, you get to a different triangle by stereographically projecting the sphere and just looking for where the 3 points go. By looking where other points go, you get a copy of the whole plane. And it turns out that lots and lots of the traditional geometry of the triangle becomes immediately evident in this picture. There's a certain set of triangles that all share a common latitude. They are what are called equicardial circles. They all have the same group up angle in the old position. It's very beautiful.